Okay, welcome back to our DTCO course. This is lecture 14. After spending some weeks for delayed lectures and also midterm examination, we are now coming back to this classroom after 2 weeks. Okay, so let's go to lecture 14. And I hope that you have already seen or watched my recorded video, lecture 12 and 13. So we have lots of things to cover today. So let's just jump into it. The last two lectures, lectures 12 and 13, were devoted to the selective edge growth. So the point was it has anisotropy originated from crystal structure. So using this current implementation of Ångström-Kraft, which is really based on a cube whose size is just 1 nanometer and 1 nanometer and also 1 nanometer, it is difficult to accurately represent this structure, but anyway we can just try to make a similar one. And I hope that already you have done some test examples for example this small sized one for these two fin structure. I assume that you have already done it properly. So now let's apply this technique to our inverter example. So for a while, so I will just skip some already existing regions. For example, in this case, dummy gates. Where can you find dummy gates? So dummy gates are running in this way. Dummy gates are not shown here because if we just display it, then entire structure is just covered by this dummy gates. And hard masks are on top of dummy gates, and spacers are just side of dummy gates, and also photoresist. What is photoresist in this case? Here we have N MOSFETs, 2B N MOSFETs, and here we have P MOSFETs, which will become P MOSFET. In this case, we wanted to separately grow something, so we must prevent this region, P MOSFET region, from epitaxial growth. So that's the reason why we introduce photoresist in this case. It is not shown here, so you can do it by yourself. And after that, now we can do, first of all, cavity etching. What is this? So here we have in its original structure, we have the line of our silicon fins. Now we have fins looks like this. However, if we just add fins on top of it, then maybe we will have some structures over this fin layer. But this is not good for our practical application. So people are doing, instead of that, first perform this kind of cavity etching. So actually, in the case of MOSFET, its benefit is not that clear, but in the next slide we will see PMOSFET cavity etching. In that case, it will be more clear to have cavity etching. But anyway, even in this MOSFET case, we perform this cavity etching. Means that originally we had the fin whose height is given as 32 nanometer. However, before starting the selective etch growth, we just make a certain shorten fin by cavity etching. So starting from this short-handed one, we will start the growth of this structure. And also, although we are not covering in this example, this cavity etching is not entirely anisotropic. Intentionally, people try to also etch the layer beneath of this spacer. Although spacers are not shown, but you can easily understand this part is actually covered by spacers, but the part beneath of this spacer is slightly etched away. So that is also good for device performance, but also not covered in this example. Here I just suggest a depth of etch as 10 nanometer, but actually I try to find out the exact value suitable for this case. Some technology shows that the entire fin itself is completely etched away in some cases. So for example, in our case, we can just eliminate the entire 32 nanometer, and sometimes it goes even deeper. That is closely related with our previous example. Okay, so I guess that we must visit well, unfortunately I have not shown here lecture 12 and 13, so let's just go to 13. If we go to lecture 13 case, then okay, let's go to lecture 12. Okay, so now you can see something. In this example, our structure starts from just a trench shown here. Here we have a trench, and what is it? Initially we had certain fin here. However, the entire fin was etched away. Even the internal fin covered by STI is etched away. After that, we start our selective epigrowth starting from this point. So that is corresponding to a certain case where we start from bottom of STI or even under the STI top level. So actually I try to find out the standard for this kind of a technique, but it was really difficult to find some well agreed one. So in this case, I just bring certain sample number like 10 nanometer. It means that still we have some remaining fin, and starting from here we grow something. And another one is now we can grow our source drain. So grow epithelial layer. Then this is the top surface of our STI, and if we allow a long time of epithelial growth, then eventually we will have something like this. This one comes from this the top left one, and also we will have another diamond and another diamond. So you can do it by yourself, and after that these three fins will be merged and used as a combined one. So in terms of resistance, as I told you before, again and again, in terms of resistance, it is good because we have a large silicon area. However, another thing we have to be a little bit careful is here we have some void, and if we have this void which is not that well controlled, then makes some problems. So in this example, I just show you that some separated fins where epitaxial growth is just stopped before they are merged. But also maybe you can remember that maybe we have seen oh, no, this was maybe we have already seen the realistic structure of for example, yes. So this is taken from Samsung FinFET, and when you have a look at these N MOSFET and P MOSFET, here you can easily see that this part and this part fins are actually merged. So they are merged in here, and also N MOSFET has merged shape. So of course for some cases it's not, but they are quite close. So which one is the standard? So I have a little idea. So that's the reason why I suggest here just to separate one. But that really depends on the technology. So please do not consider this separated fins as the standard one. Yes, here we have N MOSFET, and also we can go to the P MOSFET. So in the case of a P MOSFET, usually we make a deeper cavity etching. In this case, 20 nanometer. But why 20 nanometer is taken? So actually, engineers did some exercise. So they change the etch depth and apply selective epi growth, and just to measure the performance of the final fabricated FinFET. And they have found that if we make deeper and deeper cavity etching, then there is a tendency of improved performance. However, there is certain saturation of this performance improvement. So if we just make it schematically, if this is performance and if this is the depth of our cavity etching, then if it is ever increasing, then we can just entirely etch the fin itself. However, it is found that for one study, so that it is saturated and its value was about 20 nanometers. So that's the reason why I took this value. But please do not take this 20 nanometer as the definite number. So in many cases, people just to eliminate the entire fin. So especially for P MOSFET. So in the case of P MOSFET, things are a little bit different from that of N MOSFET. So in this case, instead of selective silicon growth, we grow silicon germanium alloy selectively. So usually the portion of this germanium contents really also depends on situation, but people usually takes about 30% or 40% content, molar content of germanium. So this is quite high, so somewhat different from silicon, and its purpose is quite obvious because silicon germanium compared with pure silicon, this germanium has a larger volume per atom. So if we just introduce silicon germanium, so by fabricating this silicon germanium, they have a larger volume. This one is a silicon germanium, and here we have underneath here silicon, and this one is a silicon germanium, and it's like a thin guy and two fat guys are just seated in a row, in a triple seat. Then what will happen? these two fat guys will just push this thin guy compressively, so this silicon channel feels something compressive stress. So this is quite much beneficial to increase especially the whole mobility. That is the main booster of our P MOSFET performance. So now you understand the necessity of PMOS cavity etching quite well. Let's say that we don't make any kind of cavity etching for silicon germanium or P MOSFET. Then what will happen? Here we have silicon channel, and if we just keep this silicon channel, then we will have silicon germanium just surrounding this silicon fin. However, the wanted direction of compressive stress is along this channel direction. So from the channel point of view, there is almost no stress applied to this silicon. I mean that, let me just draw, although my drawing is not that good, but let me just draw it. So if we just keep silicon fin here, then let's say that this is our real channel, and let's say that this is our source and drain region. And if we have, for example, silicon germanium and also silicon germanium here, let's say silicon germanium and silicon germanium, but the important direction is just this direction, channel direction, and from the viewpoint of this silicon, it is just surrounded by silicon and having no real compressive stress applied to this silicon channel. So this is not good for our purpose. Instead, we must introduce silicon germanium and also silicon germanium. So then this silicon channel feels the compressive stress. That's the reason why we must perform the cavity etching for this P MOSFET case. Later in this semester, we will talk about different technology, different device architecture called as nanosheet MOSFET instead of this FinFET. In this case, cavity etching is almost mandatory, and yes, we have completely etched away silicon cavity, source drain cavity. So we will revisit that issue later once again. But anyway, for this case, we have different depths, different options for performing cavity etching, and we do something. So you can find that the shape of this silicon germanium cavity seems to be quite marginal. So you can see that this is quite small. If we have a look at the realistic shape of this silicon germanium epilayer, then you can clearly see the diamonds, but it is not grown that well to have a clear diamond structure. So I just make a caution that exact shape may be different depending on the realistic case. And finally, I wanted to once again emphasize that this angle is corresponding to 45 degree, but this is only due to not a certain reasonable way, but this is just because we are now using a cube as a building block of our code. So that is nothing related to the physical reasoning. Okay, so now we have covered, although not perfect, we have covered source drain, epitaxial process that was quite important. So now we have filled it, source and drain part. After that, now we must do some summer process. Also, this is quite important. It means that now we have source and drain. Wow. Then how many dopants are there? And we have not covered the doping up to now. Then in this case, silicon germanium or silicon, how can we make a doping? So when we make this n-type silicon source and drain, actually we add a certain portion of phosphorus. So small portion of phosphorus is added. Why we introduce this kind of notation? So this is quite widely used. If we say silicon phosphide, it means that this one has quite a reasonable number. However, in this case, it clearly says that this is still can be regarded as a pure, almost pure silicon, and having some kind of phosphorus atoms as impurities. Please note that silicon has density of 5 times 22 per cubic centimeter. This is the density of silicon atoms. So it means that if we allow 1% of phosphorus, that is corresponding to 5 times 10 to the 20 per cubic centimeter. So maybe you remember that when we talk about arsenic doping or phosphorus doping or other kinds of doping concentration, so you can find that the density is not that high, less than 5 times 10 to the 20 or around 5 times something. So we introduced this kind of things. But point is, where can I find? So let me just come back once again. Sorry from this back and forth for my lecture materials, but it is important to understand. Not this one. So now let's go to our lecture material. Okay. So this figure shows the configuration or size of silicon atoms in the perfect crystalline silicon. And we can introduce some impurity atoms into this crystal structure. Let's say that there is one impurity atom. However, point is, if our atom is taking certain place which is not previously assigned as the position for silicon, for example, this one or that one, we can find many points. Then when an atom, impurity atom, takes this place, then they are not working as a proper impurity atom. Only when they takes the place for silicon, then they are called as a substitutional, and only when they become substitutional, taking the place of silicon atom, they become the real impurity and contribute to holes or electrons. So now let's come back to our case. when we perform this kind of silicon epi or silicon germanium epi, we intentionally introduce some portion of impurity atoms. Yes, so we have many impurity atoms, but there is no guarantee that they are taking the place for silicon atom. They are not belonging to the crystal structure. They are just aliens in this silicon system. So by applying quite a high temperature, large heat, then we can allow realign these atoms, and quite naturally some impurity atoms are moving into those substitutional sites. So that is called as activation of a dopant. So although it is written as dopants must be activated, it means that our dopant atoms should take the substitutional sites, and for that purpose we must apply quite a high temperature. So if we allow quite a long time of high temperature, say that long time period and quite a high temperature, then that will be perfect. But that should be avoided at best, because if we apply high temperature and long time, then our impurity atoms have too many chances to diffuse over our entire semiconductor region. So what we wanted to have is impurities are placed only at source and drain epitaxial region. However, if we apply too long heat process, then they will just escape from initially defined region, and they will just enter into it. So usually that is related with this one. So let's say that here we have a silicon, and here we have an epi layer, and also we have an epi layer. And usually this silicon channel is, although doped at the starting from its initial process, its range is known to be about 10 to the 16 or 10 to the 17 per cubic centimeter. So in this case, now we introduce epitaxial region. In this case, the orders of our impurity concentration is certainly higher than 10 to the 20 and 10 to the 20, but they are not activated. So we must apply something, some heat. But point is, once we apply summer process, then they become really the active dopant, but at the same time, they diffuse into this silicon region. Because we have a relatively small density and relatively high density. So please try to estimate the density difference between these two numbers. It is orders of 10 to the 3 over 10 to the 4, 3 orders of magnitude or 4 orders of magnitude higher than silicon region. So from the viewpoint of our epitaxial layer, silicon channel is just empty, and when heat is supplied, then they just diffuse into this silicon. Unfortunately, the degree of their diffusion really makes critical impact on the device performance. It means that if we have abrupt one or slight diffusion, more diffusion, and more diffusion, that introduces a lot of difference in their performance. So we must carefully, really carefully control this one, this number or degree of diffusion, and state of the art value is about nowadays just for reduction of 1 decade, means that starting from 10 to the 20, where can you find the 10 to the 19 per cubic centimeter in this doping profile? It is around 2 point something nanometer. So means that here we have, for example, 10 to the 20. And after just 2 nanometer or 3 nanometer into the channel, then doping concentration just becomes 10 to the 19. So 2 nanometer, 2 nanometer is actually corresponding to just 4 cubes in our silicon cubic structure. So if we go to 4 or 5 cubes, then the doping concentration is reduced a factor of 10. So the control of this doping is so severe, so we cannot allow any kind of long diffusion. So that's the reason why we must apply heat only quite a short time. So how short is it? It is orders of just seconds. Just a few seconds, we just introduce quite a high temperature. How high is it? In Celsius, it's around 1000 Celsius. So this is far, far higher than any other temperature in our process, and that makes quite a serious impact on the performance. It means that later we must perform this high K metal gate formation. Please note that up to now we have just make a dummy gate which will be later replaced with this high K metal gate stack. However, this one, the typical temperature of this high K is in Celsius just about 400 Celsius. So if we apply 1000 to this stack, then actually this stack just destroyed. So now you can see something here. This one is taken from Peking University's BSI symposium paper in maybe this year. So this June it was published. Yes. Here we can find two different curves. One curve is a blue curve and one curve is a red one. And this blue one is corresponding to the original structure. Oh, we have made some structure with a conventional procedure and looks beautiful. After that, only after the process is over, then the authors applied 600 Celsius heat process. So compared with the typical temperature, like 1000 Celsius, I think that this is a much reduced one. But I guess that the intention of the authors showing this graph is, well, it is not that much affected, so they intentionally introduce a relatively low temperature, but in reality temperature is even higher than this 700. And please have a look at the result. When we apply 700 Celsius heat process, blue device becomes red device. What is it? So you can see that the great reduction of on current. So although you can see that this is relatively small in this scale, but this is just a logarithmic scale, and this small difference is corresponding to 1 decade, 10 times the reduction. And this small difference, yes, this guy is corresponding to 2 times reduction. So on current is more than twice reduced by applying this heat process. So it is not acceptable at all. So we cannot endure this kind of a reduction in this case. Also, threshold voltage itself is quite much shifted. Starting from, for example, let's say this is the criterion to take threshold voltage, then you can see that about 0.2 volt difference occurs in the threshold voltage. So simply speaking, there is a rule that you should not apply high temperature once after this high K gate stack is formulated. Once you make high K gate stack, then never apply any higher temperature to your device. So that is quite important. Maybe some of you guys in our classroom have attended the colloquium lecture by Professor Han Woo, this the first author of this BLSI technology symposium paper. And in this case, the authors introduced some quite brilliant idea called as flip fed. And this flip fed introduced some concept of flipping wafers to fabricate both of MOSFET and PMOSFET simultaneously, but they have a serious drawback of swapping the process for high K metal gate and source and drain. So that is regarded as the biggest drawback of this quite a brilliant idea flip fed. So the authors introduce double flipping to avoid that kind of one. But you know, every time we make a flipping, then that is related with the reduction of processing yield. So we have to be more critically consider this option. But anyway, it is important to understand there is a recommended order between this source drain, heat process, and metal gate stack formation. And now we are almost done in this case. So before starting this dummy gate or metal gate process, we must perform salicide process. Salicide is not a standard word, but in this field, in our device engineering, this is regarded as almost a standard one. Salicide means that self-aligned silicide. So what is a silicide? Silicide means that silicon which is alloyed or combined with other, for example, metal. Here, typical metal can be, for example, nickel or titanium, or other metals can be introduced to make this salicide or silicide. But when that is self-aligned, that is called as salicide. Maybe you can ask me, what is this one? So please note that here we have fin, and here we have a fin surrounded by silicon, and later we will eventually attach metal on it. However, the contact between this metal and this one, this source drain epilation, when we just make a direct contact between metal and this source drain epilation, then we can have a quite large contact resistance. we wanted to reduce this contact resistance as much as possible. So we introduce some intermediate layer starting from pure silicon to the pure metal. In this case, we introduce a silicide resin. And for that purpose, usually nickel is widely used. So how can you make this silicide? It is quite easy. Just on top of silicon, put silicon. After that, just also apply some heat. Then this nickel and silicon makes some reaction, and they becomes silicon nitride. So its temperature is not as high as this 1000 Celsius. Its a stable temperature is known to be about 500 Celsius. So we can make this silicon nickel silicide formation. So it's good. And what we can do is just to deposit nickel all over our structure. Now we have some structure, and over this structure we just put nickel entirely. Its depth is seems to be about 10 nanometer or 20 nanometer. Yes, after that, just to apply heat, then now it becomes nickel silicide. So nickel is combined with silicon, so it becomes nickel silicide. Point is, we have some means to make a selectivity between pure nickel and nickel silicide. Now we have two materials. If this nickel is attached on top of a dielectric, then it does not react. But it is attached on top of a silicon, then it becomes nickel silicide. After that, we can selectively remove only nickel, and nickel silicide is still attached on top of a silicon. That is possible. So now you can have here we have silicide and silicide and silicide. So they can have this one. Of course, I'm saying that nickel silicide, when we have N MOSFET, how about P MOSFET? Then in this case, of course, the silicide will become silicon germanium nickel, because this guy is found in this epitaxial layer. So our silicide on top of a PMOS part will be just a silicon germanium nickel. So that is the situation we will have. So this silicide will work as a buffer between pure metal and silicon epi layer to reduce the resistance. But unfortunately, in our Ångström craft, we cannot make a certain chemical reaction. Be careful. In reality, what we do is, now we have in this case we have silicon and nickel is deposited. After that, by applying certain heat, now this nickel becomes silicide. However, when this reaction is over, then can you find, for example, a layer of nickel silicide, and still we have silicon and it has its own shape. Unfortunately, it's not, because in order to be silicide, we need silicon. What happens? So this nickel and nearby silicon are mixed up. So now eventually we have some layer of nickel silicide. So the, how can I say, boundary between silicon and nickel silicide is not exactly the initial boundary between silicon and nickel. So that is also quite frequently seen in another process, another very important process called as oxidation. So means that originally we have a silicon and we introduce oxygen atom by some means, for example, water vapor or O2 gas. So we apply anyway this oxygen atom into this silicon. Then what will happen? Now by reaction between oxygen atom and silicon atom, it becomes a layer of silicon dioxide. However, once again, when we just measure the interface between this silicon and silicon dioxide, it is not located at this point, because in order to make silicon dioxide, some portion of silicon should be consumed. So what we have in reality is, yes, there is some part of silicon, originally silicon, but that is consumed and become another silicon dioxide layer. Quite similarly, when we have this silicon originally, and when we attach nickel, then apply heat, then some portion of silicon is consumed to become silicon nitride. So its thickness becomes even thicker than the original thickness of silicon, thickness of nickel deposition. However, in our Ångström craft, we cannot make the change from nickel into nickel silicide, or so we will neglect this one just to try to mimic this silicidation, quite simple selective deposition only on top of silicon. So please be careful. So now let's go to this one. Okay, now we go to the next step. Although I have not shown here, but when we have a look at the structure up to now, I guess that you can watch your own structure. Then you can find that source drain epilation has deep cavity still. Although we have grown source drain epitaxial layer, but it is not that big. Still, we have quite much deep cavity for source drain region. So that is just covered by this layer called as interlayer dielectric, and this number is corresponding to the order of appearance. So since this is the very initial one, it is quite typically labeled with number 0, so ILD 0. Then actually what happens? So please note that this is our initial level of STI, and before introducing ILD 0, what happens? Here we have something corresponding to source drain epi. Yes, here we have source drain epi, and here we have a void, and here we have void. And this void is covered or filled with typically silicon dioxide layer, so that is covered. How can you cover it? Just to make a deposition. Then if we perform this deposition, then what will happen? So we will have some groove of a silicon dioxide layer. Because it starts from this hard mask, it will show high, and since we start from this deep cavity, then we will have low, high and low, and high and low. So this is not planarized at all, and there is a real groove. But this is not good at all, so we perform once again chemical, mechanical polishing down to the top of a hard mask. So this blue one is corresponding to our dummy gate, and this is our hard mask corresponding to silicon nitride. And initially we have also silicon dioxide layer, and this silicon dioxide layer is continuously eliminated by CMP, and after that, once this CMP front finds the silicon nitride layer, then the etch rate becomes suddenly quite slow, and we have some optical means to observe it. Then okay, now we understand. Now we have arrived at the top of a silicon nitride hard mask. Then using some slight overetch to make sure that everything is really well exposed, then we can make this very beautiful structure. When we make a top view of this structure, so starting from this seen from this top view, then what we can see is just the entire our cell is covered with silicon dioxide corresponding to ILD0, and only for the position for our dummy gates you can find some part which is exposed as silicon nitride. So that will become our current situation after ILD0 filling and CMP. So now we are ready to eliminate this dummy gate, because now we have a quite clear material difference between this silicon dioxide and silicon nitride. What we can do is selectively etch silicon nitride. Then what will happen? So silicon dioxide is just kept, and we will have just we will find the top of a dummy gate, and this is sometimes polysilicon or amorphous silicon. But even though we start from amorphous silicon, after applying some heat, they becomes a polycrystalline silicon. Yes, you can find the polycrystalline dummy gates, and they can be also selectively etched away. So that will be discussed later. But we have another step before we performing this dummy gate formation. So replacement metal gate formation, gate cut. So this is not well discussed in other courses, so please have a look at this one. This is our current structure, but you can find that this yellow one is corresponding to the nitride, but nitride hard mask. But initially we have drawn dummy gate in this way, horizontally. there is no cut of our dummy gate, because this is related with the difficulty of certain line drawing. So please think about our fin formation or dummy gate. In order to perform this kind of uniform structure, we had to perform self-aligned double patterning or self-aligned quadruple patterning. So in that case, make any kind of stopping here, it is almost impossible. So our initial structure just looks like the ever running lines in a vertical direction. Along y direction, we have a long line of dummy gates. Then what happens? So we know that this part will become an inverter. And let's say that we have the next cell, and also it will become another inverter. Then this one has its own input signal, and it has its another input signal. If we just keep this long line, and if this one becomes just the same metal gate, then they must share input voltage. So it's not desirable at all. We need to separate input voltage, output voltage of these two neighboring cells completely. So we need to eliminate this part. Here, the dummy gate should be eliminated. So that is done here. So also I have dig out the progress of our fabrication technology. So where we perform gate cut, that is also a matter of choice. At the beginning of our FinFET technology, the gate cut was performed even earlier. But in the case of this FinFET, this is the standard standard position to perform this gate cut after silicide. And if we dig out another research paper, then we can find some attempt to even delay the gate cut after, for example, RMG. So after metal gate is once fabricated, then they try to cut this metal gate. Once make a metal gate, then cut it. This is another approach. So I'm not so sure what is the most advanced one, but in this 7 nanometer FinFET technology, this is the typical standard position where we perform this gate cut. Anyway, dummy gates are originally running over several logic gates. Here below we have another logic gate, and also of course here we have another logic gate, but they should be separated. So for the gate cut reason, etch the hard mask and dummy gate. Then can we just selectively, let's say that here we have a hard mask and select only this one. Is it possible? So it's not possible because this is just 20 nanometer wide, and it is also around 20 nanometer. We cannot pattern that kind of quite small sized dot in this technology. So what we do is just to consider certain amount of width for gate cut, and also gate cut is done as a long line. So it means that now here we have a certain island of a logic gate, and also the lower one is separated by, here we have another logic gate, and they are separated by this gate cut. So how much can you make this shallow or short gate cut? That is directly related with reduction of our chip area. Although this gate cut is not used as the real device. So where can you find the real device? Only here we can find the real device, and any interesting thing occurs only here. However, unfortunately, we must isolate each logic cell, so we must introduce some buffer between them for isolation. So this is required. In our example, we introduce this 31. So this is the position for gate cut. Starting from 0 up to here, we have a 31 nanometer. Compared with even shorter length scale, it has more margin. So we will have this gate cut. So when gate cut is done, now previously there was a long running lines. However, they are now separated, and when we just becomes this silicon oxide invisible, then now you will see this one. This one is just the same structure without displaying silicon dioxide. Yes, this is still our dummy gate, and it's a hard mask, and this one is corresponding to spacers. And yes, this is spacers, and this guy is the silicide for P MOSFET, and this guy is a silicide for our N MOSFET. Later we will have a P MOSFET here and N MOSFET here, and these two surrounding gates is just a dummy gate to isolate this structure with the one in the left side and right side. Okay, so still we have to also do CMP again. Simply speaking, we can eliminate this hard mask and dummy gate. After that, there is a cavity, and this cavity is once again filled with silicon dioxide, and you can see that there becomes another non-polar planarized surface, so that is CMP once again. In this case, the height of CMP is again this hard mask. The top of hard mask is set as the etch stop height for our CMP. So now you understand very important lesson from this one. Who decide the height of ILD0? Starting from our STI. Of course, we have fin height. After that, we introduce certain dummy gate. So dummy gate running, and here we have a dummy gate. Its height is about 90 nanometer or 100 nanometer, but this one does not determine the height of our ILD0. Actually, the height of ILD0 is determined by, on top of this dummy gate, we introduce hard mask, and this hard mask top surface really determines the height of later ILD0. Of course, we have a slight overetch, but therefore just mere sum of dummy gate height and hard mask thickness becomes thickness of ILD0. It's not, but anyway, this is quite important for our ILD0 thickness. So I'm afraid that I cannot cover all of prepared material, but anyway, let me just try. Now we have well separated, well cutted gates, and now we eliminate dummy gate. In order to eliminate dummy gate itself, polysilicon, first of all, we must eliminate hard mask. So using the selectivity between SiO2 and silicon nitride, it can be easily done. Once after hard mask is eliminated, then now we can see polysilicon, and also using the selectivity between silicon dioxide and polysilicon, also we can eliminate dummy gate. Then what happens? Now you have this structure. Actually not. Even though you have eliminated hard mask and polysilicon, still on top of this silicon region, we have dummy dielectric. So because when we start our entire procedure, we first introduce about 2 nanometer thick dielectric layer, silicon dioxide, to protect our very precious silicon fin. So that also should be eliminated. So then, yes, dummy dielectric is also etched. Then only after that, now we can have exposed silicon fin. This exposure is very important because now this silicon will become the channel, and we have to make very high quality high K stack, dielectric stack, starting from this silicon, quite clean silicon layer. Now we go to high K stack. So we wanted to introduce high K stack. High K stack is usually thought as just this one, silicon, and usually kind of a hafnium oxide with some additional components. And here we have also very thin layer of silicon dioxide. This thin layer is called as interfacial layer, and its thickness is known to be about just 0.5 nanometer. So we have to have a very thin layer. This is corresponding to just 1 cubic cubes of a silicon crystal structure. For that thickness, we introduce a silicon dioxide layer. Unfortunately, in the current implementation of our code, Ångström-Craft 0.5 nanometer cannot be resolved at all. So we just assume that the minimum length, 1 nanometer. First of all, make 1 nanometer thick interfacial layer. But that is just oxidation, not depositing silicon dioxide. So deposition sometimes can be done without selectivity. We can deposit something all over some places. However, in this case, we intentionally perform this oxidation, and only silicon is now converted into silicon dioxide. And now we have in our example code, So we can just perform depositing 1 nanometer thick silicon dioxide layer only selectively on top of a silicon layer. That is just mimicking this is oxidation process. Please understand, right now we cannot make such kind of silicidation or oxidation. This kind of material conversion cannot be covered. So instead of that, we just assume that that is attached on top of existing silicon. After that, for the same position, we just add 2 nanometer thick high K layer. Oh, but here we have some differences between interfacial layer formation and hafnium oxide high K layer. Interfacial layer is done by oxidation, so only silicon becomes silicon dioxide, but hafnium oxide layer is just deposited, so it covers everywhere. For example, when you have a look at this structure, this part is corresponding to hafnium oxide layer, and this is just a silicon dioxide. Even on top of this silicon dioxide, we just add a hafnium oxide. Do you want to have this one here? Actually not, but still we have it. So I think that the time is over, so let me just finish it here. Although we have this structure, now we have a spacer, and silicon. In this case, in high K, we grow silicon dioxide only on top of silicon. After that, hafnium oxide is deposited. Then this deposited hafnium oxide can cover even spacer. That is the shape of our high K material. So please remember this one. Okay, originally I assigned one homework problem to you, but I think that I have not covered the remaining slide. So there is no official homework today. We will just cover the remaining lecture contents. After that, you will have homework. But since there are so many steps already covered today and to be covered in lecture 15, so please prepare yourself to catch up today's lecture progress using Armstrong Craft. Okay, if you don't have any further question, then I want to wrap up today's lecture.